All right, guys, so in this video, we're going to talk about logarithmic differentiation. But before we get into that, I just want to review the properties of logs with you guys, or at least three of them. The first one is what I call the power rule for logs, where we're able to take this exponent here and actually bring it down in front of the log. The second one I'll refer to as the product rule for logs, because we have a product x times y here, in which case we can split it apart now into a sum. And then the quotient rule for logs can be split apart into a difference. So power, product, and quotient for logs. You should have seen these in college algebra. If it's been a while, you can always go back and rewatch my college algebra videos. And I would also encourage you to do so for another reason. In my videos, in particular the one titled Logarithmic Functions Part 1, so Logarithmic Functions Part 1, I actually prove this property right here as well as this one. Rules number 2 and 3 generally don't surprise a lot of people, but the first one up here, this power rule for logs, raises a few questions from time to time as to why that's legal. And so if you go back and you rewatch this video, I will prove that for you as well. So I think that's definitely worth your time, especially for a Calc 2 student. So if you're good with those properties, I'm going to go ahead and clear the screen and we'll talk about logarithmic differentiation. Okay, so now we're ready to talk about logarithmic differentiation. And so I've got a function up here on the screen that we are going to find the derivative of. And normally when I put this problem up in front of the class, everybody looks at me like I'm crazy, like I'm not going to take the derivative of that, that's horrible. Well, it might be using some of the earlier techniques, but now that we have logarithms available to us, we can simply start this by logging both sides of the equation. So I've got my natural log and natural log. We've got our square root of x, e to the x squared minus x, and an x plus 1 to the 2/3, all now inside that natural log on the right. So now, because we have that natural log there, we can actually use our properties that we just discussed to expand out this big mess. Okay, so what I see is, I see three products. I've got this times this times this, and I also know this has an exponent of 1/2 that can be brought down in front of its log. This exponent can be brought down in front of its log, as well as the 2/3 in front of its log. So let me expand that out for you here. So I'm going to have this 1/2 natural log x plus an x squared minus x natural log e plus a 2/3 natural log of x plus 1. So now we've been able to expand that out using those properties, and individually these derivatives are going to be quite simple, especially compared to what we would have had to deal with up here without these logs. Okay, so at this point now, real quick observation, the natural log of e is 1, so that's just a constant that I don't really have to pay attention to. In this particular term, all I care about is that. Okay, now we're ready to take this thing and ddx both sides. So on the left, the derivative of the natural log is going to be 1 over the y back times the derivative of the inside, which would be the derivative of y with respect to x, so dy dx. And on the right now, we'll go term by term. We'll have a 1/2 times 1 over x for that first derivative, plus now we'll have a 2x minus 1 for the second term, and then plus a 2/3 times the derivative of that natural log, which would be 1 over x plus 1, and the derivative of the inside of this with respect to x would just be that 1 that we don't necessarily need to write. Okay, so here is a good example of how simple this derivative can be by applying these logarithmic properties. Now, we're not quite done yet. Our goal was to find dy dx, so I'm going to need to multiply that y to the other side. I'm not going to clean it up too much here, but I will just go ahead and combine at least the multiplication of those fractions. And then I'll move the y to the other side like I talked about. And now we're going to substitute the y value back in. Remember, y was this thing right here. So I'm going to take all of that and I'm going to replace it right there from that y. So our final answer now, at least a nice unsimplified final answer, would be what we had from the previous step, but then multiplied by the root x times e raised to the x squared minus x times x plus 1 to the 2/3. So it's a pretty ugly final answer, which probably isn't too surprising considering how ugly the function was here. If we did a triple product, as you can imagine, it would have gotten pretty nasty as well. So bottom line is, using these logarithmic properties, it sure made the calculus of the problem a whole lot easier. All right, so the last thing I want to do in this video is actually go back to a Calc 1 concept where we talked about this power rule for a derivative. We know from Calc 1 that if in any case you have this function, you can define its derivative, you multiply the n down, and then you subtract 1. In Calc 1, I proved that using the binomial theorem, which wasn't a terribly difficult proof, but it was a little bit messier than it needs to be now at this point that we have logarithmic differentiation. So I'm actually going to prove this again for you. So we're going to start by letting our y equal x to the n, and I'm going to go ahead and log both sides just like I did in the previous example. Again, we're doing this by logarithmic differentiation. Having logged it, on the right, the n can come down, and then I'll have my natural log of x off to the side. I'll go ahead now, d dx both sides. And just like the last one, on the left, I have this 1 over y dy dx. And on the right, I'm going to have an n times a 1 over x. Well, now, when I move my y to the other side, I'm going to have this n over x times y. And we know that that y value up here was defined as x to the n. So we have an n over x times x to the n. Well, remember, this is an n to the first down here. So when I want to combine these two things, since I'm dividing, I would subtract the exponents. So by subtracting the exponents, that would give me my n times x raised to the n minus 1, as we expected from what we learned in Calc 1. So a much more direct, much easier, less messy proof of that chain rule for the derivatives, fully taking advantage now of logarithmic differentiation.